Hi guys, welcome back to the channel. In this video we are going to discuss the decoder applications. So let's start. So we have some applications here. So these are the things that we are going to discuss except the 7-segment display. So the first one is code conversion, implementing other logic circuits, address decoding, generation of control signals. So these four implementations or the applications of decoder we are going to see in this video. So first let's start with the code conversion. In the code conversion also we are going to see these three conversions. So because this is decoder, if you give n inputs we are going to get the bigger one, that is 2 power n outputs. So we are always going to send the binary inputs and we are going to obtain the higher ones, that is octal or decimal or hexadecimal we are going to obtain in the output. So these three conversions we will see in this video. So let's start with the first one, binary to octal conversion. So as this is the octal, in the output side we need to have 8 outputs. So for that purpose I need to take the 3x8 decoder. So I took 3x8 decoder. So I hope you know this. So octal means what? 0 to 7. We have total 8 terms in that. So I also represented in binary and the corresponding octal as well. So the output terms, that is from D0 to D7, I directly write the octal expressions or octal outputs, that is from 0 to 7, the same thing. So I also wrote the truth table or the 3x8 decoder, you can observe there clearly. So conversion is nothing but simple thing. So if you want anything as output in the form of octal, you are going to send ABC in the form of binary. If you observe in the table, we have total 8 combinations from 000 to 111. So any of this combination if you pass there, we are going to select one line, that is the line, the output that we are going to get. Suppose if you select 111, we are going to get, or the line selected is D7. So answer is 7, means octal, in octal that is 7. 111 means 7. Yeah, this is the thing I am saying about if you pass 111. So in this I have the changed thing also. In the output the 7th line is selected, or the line 7 or the 8, that is in the position 8 this selected, we are passing 111. So we can say simply that is 7 in octal form. The second example, if you consider, that is if you pass 010, that you are going to select the line 2 or D2. So according to D2, that is 2 only in binary to decimal conversion if you convert. So 2 is our output in octal form as well. The next conversion we are going to see in the code conversion is binary to decimal. So we know already decimal means 10. So I have drawn the 4x16 decoder. So we have 4 inputs and 2 power 4 means 16 outputs, but we do not need all 16 outputs. We just need the 10 outputs, that is from D0 to D9. So we are going to trim all the remaining things off. So we are going to have 4 inputs and 10 outputs, and the remaining outputs are don't care conditions. So after trimming the remaining from D10 to D15, this is the remaining 4x16 decoder. If you observe that we are having 4 inputs and total 10 outputs. So as we are converting to decimal, that's why we have done like this. But the remaining outputs are also there, but we don't consider them. That is known as don't care situations. So if you consider the decimal that I have represented with the help of binary, and decimal also means 0 to 10 or 0 to 9, we can say total 10 outputs. Correspondingly, I have represented from D0 to D9 also. So this is also simple conversion as like that only. So if you observe, I have replaced from D0 to D9 with all the decimal numbers from 0 to 9. So you can observe, you can pass any of the, means if you observe there from 4 zeros to 10001, that is from 0 to 9, you can pass any of the binary from in the variables, that is A, B, C, D. You can pass in that and you are going to obtain the corresponding decimal. That is the required thing that we want. If you observe 0101, that is in binary, that is if you convert to decimal, that is 5. If you convert that 1001 to decimal, that is 9. Means the 9th line or the 10th position I will be selected, I can say simply. If you want to draw the circuit diagram for the binary to decimal, so this is the circuit diagram that you can see over there. So we have 4 variables A, B, C, D, but it is trimmed, not full. So we are not going to up to D15. We are going to just from D0 to D9, that is total 10 terms. 10 terms means total 10 means 10 AND gates we are going to require. So according to the truth table, if you observe A, B, C, D and outputs from 00000 to 1001, that is D9, we are going to all have the AND gates. But the remaining things that you can fill in between. So if you observe the first one, that is A bar, B bar, C bar, D bar in that is in the SOP format. So you can connect like A bar, B bar, C bar, D bar according to the circuit diagram you can see over there, and D1 means A bar, B bar, C bar, D bar, and you can connect it like that, and up to D9 as like in between also you can convert like that only. So this is the last conversion in the code converter first application. So binary to hexadecimal. So if you don't know hexadecimal, let's see a quick overview of the hexadecimal. So hexadecimal means 16 2 power 4, octal means 2 power 8. So hexadecimal means 16 means we are going from 0 to 15. So actually we are going from 0 to 15 means total 16 terms, but double digit is not allowed here. So binary we are going normally we are going from 0 to 15 in binary, that's not a problem. But if you are not in decimal, you should not go like that. You have to go from 0 to 9, then after 9 you should not take double digit, then you need to start with alphabets, that is from A, B, C, D, E, F. So you can also observe that I directly took 4 cross 16. So in this case we do not have any trimming here because we need all the 16 outputs because this is the hexadecimal. Here you can observe the truth table or the 4 cross 16 decoder. You can compare that ABCDs, that is 000, that binary, and normal D0 D0. You can compare both of them and you can relate. So finally you can represent in a simple manner from 0 to 9 and A, B, C, D, E, F in the outputs. So for the simplicity I am representing these things. So in the inputs I am passing A, B, C, D. So if you observe, the conversion is very simple. So in the previous slide you are going to have some according to the truth table. So suppose if I passed in binary, that is 0101 in ABCDs. So I am going to obtain, that is in the binary you are going to convert simple to decimal, that's it. Then next is 0111, that is 7, we know already, that is 111 means 7 only. Next one, that is 4 ones. 4 ones means what? The last one will be selected, that is F. So in this case, as this is hexadecimal, so we are not going to represent with D15. So here is hexadecimal, so simply that is F. So 1010 means 10. So 10 is not possible. So in this case we have A, so A represent A. That is our final answer in hexadecimal. I forgot to mention that the first one is very important, that is code conversion. The first application is very important, and the second application is also very important, that is implementing other logic circuits. So if you also observe, with the help of decoders we can perform or we can implement any other logic circuits. So first let's see how to implement the full adder circuit with the decoders. So if you observe, this is the truth table for the full adder. So I took sum and carry, so where there is min terms, that is 1, I am going to circle that. So as here we have 3 variables and total 8 terms, we are going to proceed with 3 cross 8 decoder, because in this also we are having 3 inputs and total 8 outputs. So if you observe the sum where there is min terms, that is 1 position, in that place, that is our output. So we have to combine all of them with the help of OR gate, and we need to have the output as sum. That's a simple thing that I can say. So if you observe, we have min terms in the positions 1, M1, M2, M4 and M7. In that decoder also you can see D1, D2, D4, D7 are connected with the help of OR gate, and that says our sum output expression. So this is the simple implementation we can say. So this decoder only the full adder circuit that we can simply convert. In the same fashion, if you want carry to be implemented with the help of decoder, just where there is min terms, there you need to connect with the help of the OR gate. As you seeing there, we have min terms in the M4, M5, M6 and M7 positions. So just convert to OR gate. So that is our final carry output with the help of decoder. So next implementation we can say that is known as event parity checker. So event parity checker means if the inputs contain one odd one. Suppose if you take the first one, there is no ones at all, so output would be 0. If one odd one is present, like in the second one, odd, that is one odd one, so that is one output we can say. So you can see that 0 1 0 is also one odd one, so that also we are going to have one. So if you see the next one, that is 0 1 1, so we have even ones, so don't do that, that is 0. So likewise, where there is odd ones, so output would be 1. So this is known as event parity checker. So if you observe the last one, we have 3 ones, so that is odd number. So ordinary number of ones. So we are in the output we are having 1. That is 1. So this can also be implemented with the help of the decoder, 3x8 decoder. So where there is one, combine all of them with the help of the OR gate. So that is the simple thing that I can say, as we already saw in the full adder and carry sum as well. So we have saw 3 implementations up to now, or any implementation that they might give. So suppose they have given like this, suppose majority of the terms are like this. So if you observe 1, 2, 3, means M0, M1, M2, and directly M5, M6, M7, they have given majority of the terms, min terms. So we need to have the OR gates. So in the current situation or in the market, we are available with only 2 input OR gate or 3 input OR gate. So 6 input OR gate is rarely available. So we are going to proceed with 2 input, means through 2, 3 input OR gates, and directly I am connecting it. So we can also connect the 6 at a time with the help of OR gate, but this is also true. Remember this, in the market what we are available with, we have to proceed with that only. These OR gates are very simply available, so I am representing in this format, so that and these formats are same. So if you observe clearly, I am connecting all the terms, that is D01, D2, D5, D6, D7 with that. So I am going to produce Y. So instead of representing all these big terms, we can simply represent with the help of the NOR gate. So let's see how to represent that. I hope you can see this now. Instead of representing the main 6 terms, you can simply represent the remaining terms, that is D4 and D5 with the help of NOR gate. NOR gate means what? Sum and reverse it. So basically again we are going to obtain the same output Y as the truth table says. I hope you can relate the NOR gate implementation. So this is the second thing or second application of decoders, that is implementing other logic circuits. Likewise, we can implement any of the logic circuit with the help of truth table and with the help of the 3x8 decoder or 4x16 decoders. So the next one is address decoding. So address decoding means, suppose if you see here, we have a microprocessor and we have a decoder and we have some chips, memory chips. Suppose, so at each of the decoder block will be selecting one of the memory block, and microprocessor will select any of the 4 blocks. So not any of the 4 blocks. Inside the blocks in 256 locations, it will select one location. So suppose example, if A9 and A8, suppose it is 00, it will be going to select M1. So in the microprocessor we have from A0 to A7, according to that we have 256 locations. So according to A0 to A7 the inputs, so in that M1 position only we have 256 locations, in that it will select one. So that we can, it is very simple, with the help of decoders we can select one, and with the help of microprocessor, the decoder only, we can select one of the location that we want, that is address decoding. Finally, we have generation of control signals. So if you see here in microprocessor only, we can control the signals, because in microprocessors we have many inputs, so many outputs also. So we have many outputs, so it is very difficult to control all the signals. So for that control, we need to have some decoders. So to control many of the other signals, like brain function, we can simply say. So these are the applications that we can say. In the upcoming video, I am going to cover the 7-segment display also. I hope you understood. Thanks for watching up to now.